Good afternoon, everyone. It's the first time I have to hook myself so I apologize for a little delay. I am Filip Novotný from Czech Technical University, and in the next 30 minutes, I would like to tell you something about my utilization of Mathematica in image processing and exactly in the measuring of electron microscope micrographs and analyzing the particles contained. So the brief outline of my talk, just a few words about the noble metal nanoparticles and what they present to today's technology, and what are the critical parameters for exploring their properties. Then I will move to the Mathematica approach to the plasmonic particle analysis, which will be presented as a simple image browser made in Mathematica, made as a Mathematica notebook, and later more advanced Mathematica app, which will be used for particle analysis, for programmatic particle analysis. And if there will be more time, in the end, I would like just to show you how to turn Mathematica notebook in something which looks for a normal user, which doesn't know Mathematica like a normal application. So to begin with, the plasmonic nanoparticles, the most pronounced example is the colloidal gold, which is known for many thousands of years already, or many thousands of years from the ancient China. These are small particles, tiny enough they can be dispersed in liquid, and even if they are gold, they are much denser than water. They didn't fall down, they didn't sediment, because they are small enough that the molecules of the solvent of the water just shake them enough to be continuously dispersed. They have very interesting optical properties. Apart from what we would expect from gold, the image of the vial contains dispersion of 20 nanometer big gold nanoparticles, and the ruby color is the actual effect which intrigued humans since the ancient China, that they thought that this kind of gold has some mystical properties, some mystical healing properties, which weren't confirmed today. But because the people drink it throughout the whole time, we know that the colloidal gold could be used as a like utility, as an agent in the living organism to transfer other kind of medicaments, for example. The interesting things about the particles is the emergence of plasmon resonance, which is as oscillation of the localized electron cloud on the metallic particle, and more importantly, the shape matters in this kind of things. So when you are able to prepare different morphologies of the nanoparticles in the solution, it enormously changes the optical properties of the solution. In the first order, you can see it by just naked eye. So there's a possibility to connect the characterization of the particles in the solution to their color. Of course, to do this, you need to have some big amount of data of how the particles and which shapes produce different, what colors produce different shape of the particles. And so you need, the only thing you can do today is take an electron microscope, which see the morphology of the particles, and try somehow count each of the particle, its size, its shape, and get some statistical number for each colloidal solution with statistically large number of particles. And this is exactly what I do in Mathematica. There are several course of open source and commercial packages or softwares to do this. None of them does everything I would like to have. So this is the motivation why I prepare the code in the Mathematica. What do you need? Usually is you need to first filter the digital images, which are often noisy, because the electron microscope, although they are very advanced, the technology applications of the nanoparticle technology uses different kind of substrates, such as glass, which can be used in modern electron microscope, which are specialized in to be able to take very nice images of the nanoparticles, but on very specialized substrates. So there's still a big need, technology need, to characterize the particle in a very noisy images, as I will show you in the following slides. So the first thing one usually do when he discovers this kind of problem, he wants to measure a few particles by hand. This can be done in Mathematica very, very easily by preparing this kind of dynamic environment, which is actually a Mathematica notebook, a window which has been stripped of the usual cell background, cell helpers on the side, and which can act as a simple image browser, with the difference that you can take calibrated measurements inside the image. This kind of functionality can be done within a single dynamic module. So I will try to show. And you just create a document, a new notebook, just from your code, using a single dynamic module containing all the functionality, with the very neat possibility which Mathematica gives you, that the dynamic module can have initialization of the definition of your functions at the beginning of the call of the dynamic module, specified as root delayed. So then the initializations are called every time you open the notebook again. So that this way you can actually define your functions in the single file, and can have the functionality of the application in a way that you can save your work, as I will just demonstrate now. I will save the notebook in its, like this, image 1. I will kill the restart the kernel. Hopefully it will work. So now I'm starting fresh with fresh kernel. And you see I have the data, and all the functions, all the definitions are working, were stored locally in the notebook. So in this way, you can create very, very cheaply in the amount of coding you need to write. Thanks to Mathematica, localization of variables, you can create this kind of application-like notebooks, which allow you to store your work in like a notebook, like a single files, which contains both the coding, and also your data. Of course, you can then program that you can change the measurements, and of course you can export them, which I just use like the export to the internal Windows memory. So this can be the basic functionality you can do very quickly in Mathematica to measure the particles in electron micrographs. Of course, the next step is to make Mathematica to measure them automatically. And this is actually a field where there is the common software for particle the resolving of the particles have some problems with different shapes, which is actually for the colloidal particles made of noble metals is the critical parameter to be able to determine the shape of the particle and more parameters. Usually, and with measuring the parameter, the diameter of the equivalence field radius of your measured particle, which is actually not good parameter from this kind of experimental materials. So the question is, can I just make Mathematica to do this, for example, to be able to measure rod-like particles, to be able to resolve the aggregates automatically? And what I want to show you that, of course, you can do anything in Mathematica. It just takes some of time. I will try to run it in the version 10. It will be a little surprise if it will work. So this is not yet ready in the form of the application notebook. This is just normal notebook appearance, and in the end, the application GUI, the graphic user interface, is contained within one manipulate and tab view. The processing workflow of this kind of electron microscopy images can be following. First, you need to filter the image, the noisy image, to be able to make either binarization or edge detection of your particles, to be able to resolve the boundaries of the particles and resolve these individual particles from the aggregates. Then you would need to select the morphological properties you want to compute for each of the particles. And most important things, which I think is very important and it's very problematic in normal softwares, is to be able to have the possibility to post-process the automated result, to be able to handpick selected aggregates which were, for example, which weren't, for example, found by your code. So we'll try to reproduce that result in the Mathematica application, where I load some image, microscopic image. You can see in Mathematica you can do several types of custom control, which this is just modified gauge control, where on the background of the gauge is used to produce the histogram of the image levels. So these are the easy ones. And following, you can prepare this kind of working environment in Mathematica, where you just select the portion of the image where you want to tune your filters for the filtering of the image. And then I think it's very, very handy to use the mathematical dynamic functionality to be able to tune the filters to your needs, because otherwise you will spend sometimes iterating the commands, and this is not usually the quickest way when you are working with new sample. So this way I can select this is the original image, and for example, first I select some noise filtering filters, try to tune it. You can see the dynamic response in the selected window, sub image. You can of course compare it. It's easy in Mathematica to do the comparison of the two images overlaid on top of themselves. And just to quicken it up, of course I have this kind of images already found on the best approach, but then I will apply some kind of sharpening. And in the end, through the edge detect function, I would find the borders of the detected particles and fill them to get the final final binarized image, which could be again checked against the original if it works. What is good functionality which can be implemented by Mathematica very quickly is that, of course, when you layer more of those filters on top of them of each other, the computation will slow down because with every movement of the dynamic slider, you recompute the whole image. You can implement this kind of freezing of the first layers of your selected filters, so they are computed and frozen. You can change them, but you can play with the last filter and have the computation more real time. Anyway, when you are satisfied, you just create the binary for the whole image and move to the next step, which will be the selection of the morphological properties you need to compute. So that is just for checking the final image, which is highlighted by the binary image. You can see the particles are nicely resolved. Here is the selection of the morphological properties. And we can measure the components for each particles, which is just the utilization of component measurement functionality in Mathematica. I think there's something around 900 particles, so it takes a while. I've entered some number of properties. We can move to what is, in my opinion, the most important part, because there you can get the immediate feedback on the selection of your parameters. And you can see all the parameters you selected to be computed for each particle in a histogram view, where you can see, for some example, some parameters like the bounding disk coverage. You can see that there is some division, some multiple sets in your particle ensemble, which of course corresponds to the different shape in the images. So this is the way how you can programmatically then find the parameters, how to differentiate the shapes of the particles. You can try to tune, and you should see dynamically changing the ensembles which are selected. So I will try to select the spherical ones. And of course, you can also implement the functionality to handpick some of the particles you couldn't find very quickly. For example, this is some kind of aggregate. I can click on it, so it's omitted from the final analysis. And also very handy is to visualize the distribution of the particles in this kind of two-dimensional parameter plot. For example, I can select this kind of axis, which is good information with the connection with the images. You can see you can now click even in the 2D plot on the point you want to omit. You can see them where they are located in the image. So in the end, this really speeds up the finding of the right conditions for the exact parameters of your measurements of the exact colloidal sample, which of course differs on both the method of the preparation of the sample for the microscope and then the methods for the analysis. Then you can move. It's then really easy in Mathematica to prepare, for example, this kind of report of the image. So you can see the spreads of the parameters, the yields of the rods, of the spheres, and you can of course join more images together for this kind of analysis. So this is the main functionality. I'm very happy I can do this with Mathematica reasonably quickly, thanks to its very neat dynamic controls. A lot of the things you have very fast, thanks to the manipulate construct. So I think this is for me it is very nice utilization of mathematical possibilities. Now we have still some minutes to, I think 5 minutes or something like that. 1 minute, five. So there's still the part where we can build a small, I can exactly show you how I prepare the application notebook, or of course, first I would like to know if you have any questions for this kind of particle utilization of Mathematica.